Hi, everyone. Welcome to the 57th session of the MedAI Group Exchange sessions. This week, we have Arjun Desai here from Stanford to speak about his work on leveraging physics-based priors for label-efficient, robust MRI reconstruction. So Arjun is a PhD student in electrical engineering at Stanford, and he's advised by Akshay Chaudhary and Chris Ray. His interests lie in the hard intersection of signal processing and machine learning, including representation learning for multimodal data and developing data efficient and robust machine learning methods. And he's also heavily involved in designing scalable clinical deployment tools and validation systems for medical image acquisition and analysis. So thanks so much, Arjun, for being here with us today. And before we start, do you have any preferences on how you'd like to take questions? Is it okay if we interrupt you, or do you prefer them all at the end?
Yeah, definitely feel free to interrupt me as much as you like.
Awesome. Okay, so let's try to make this as interactive as possible. And without further ado, let me hand it over to Arjun.
Awesome. Well, thanks, Nandita, and appreciate you inviting me to speak about our work on what we're doing on building these label-efficient, robust MRI method or MRI reconstruction methods. So a lot of the work that I'll talk about today was done with several research and clinical collaborators, without whom this work would definitely not have been possible. So we'll just jump right in and start by talking about what is MRI reconstruction and why is it important, as well as what are some of the challenges that we have of existing methods that are trying to solve this task. And then later in the presentation, we'll shift gears a little bit to talk a bit more about how we can address some of these challenges by thinking about data from a physics-driven perspective, particularly thinking about how data is generated based on the physics of the imaging system. And we'll use this perspective to motivate some of the different hammers that we built to solve this problem. And three of the ones that I'll talk about today are Noise2Recon, VORTEX, and the newer version of Noise2Recon called Noise2Recon SS, which is a self-supervised extension of Noise2Recon. And finally, we'll end with some takeaways and conclusions about this work and how it can inspire us to think about MRI reconstruction moving forward. So MRI is quite a powerful imaging modality because it gives us quite high resolution images and excellent soft tissue contrast. The issue with MRI is it is extremely slow. And you can think about if you're a patient sitting in a scanner for over 30 minutes to an hour for kind of a single or series of MRI scans, it will be quite uncomfortable for you, especially those that are claustrophobic. So a key important problem in MR is how can we accelerate our scans in order to increase our imaging throughput and the overall operational efficiency of performing MRI. And more recently, deep learning methods have shown quite a lot of promise for MRI reconstruction, particularly at higher acceleration factors. So the acceleration factor is how much do we accelerate our scans by? So if we accelerate it by 2x, that means our scans are twice as fast. And if we are able to push these acceleration factors more, our speed up time is greater, and that's beneficial for the overall acceleration process. So to accelerate our scans, the raw data, which is typically acquired with multiple coils or sensors, is undersampled by a preset undersampling mask. The naive reconstruction of this undersampled data suffers from signal aliasing, which results in a degraded image. And the goal of our reconstruction methods is to recover the high resolution images from this aliased image. And it's important to remember that these high resolution or high quality images are not only important for the downstream radiologist readings that we may want to do, but they're also important for other downstream image analysis tasks that require high resolution inputs. So these can include things like pathology detection or tissue segmentation. And while a lot of these deep learning methods have shown quite a lot of promise for reconstruction, their translation into clinical practice has been somewhat limited. And there's a few reasons for this. The first is that the vast majority of reconstruction methods today are fully supervised, which means that their performance is primarily limited by the amount of available fully sampled or labeled training examples. And in practice, we typically have far fewer labeled or fully sampled scans compared to the number of prospectively accelerated or undersampled scans that we can acquire from the clinic. Another key limitation that seems to be plaguing several deep learning methods out there, so this is not unique to MR reconstruction, but these deep learning methods are typically very sensitive to shifts in data distribution. And particularly for deep learning methods for MR recon, we see that standard perturbations that occur as part of the imaging, MR imaging process cause drastic degradation in the reconstruction. So if we have changes in our signal to noise ratio or SNR, where the patient moves during the scan, the reconstructions that we get are very, very low quality. And the fact that these perturbations occur almost routinely in clinical practice, if we can't be robust to them, it's difficult to justify deploying these models safely in clinics. So what we're really interested in building are these MRI reconstruction methods that are both label efficient as well as robust to these physics-driven perturbations that occur frequently in the MR acquisition process. So by this, I mean that we should be able to train our models with limited amounts of label training data. So when we don't have access to a large number of fully sampled scans, and we want to make sure that we can generate high quality reconstructions, even in the presence of these clinically relevant distribution shifts. So these two kind of properties or desiderata that we're looking in our models seem to be quite orthogonal, but they really boil down at their core to a very central question, which is how do we teach our models to estimate a broader data distribution without access to the relevant data or mappings between inputs and outputs? And kind of the short answer to this is that we can use data priors. And priors are properties of the data that we expect our data to have. And we can use that as a regularization method when we're doing our optimization. So one of the priors that we pose as being quite important to this problem is how do we think about data as a generative process? And in particular, how do we think about data generation as a function of the physics of the imaging system? So if I'm trying to take an image of a very cute dog, I'll typically have some camera that takes an image of the target. So the signal from the target gets pushed through this imaging system, and we get some observed signal, right, which is the photograph that we acquire. And sometimes this photograph is blurry, or it may have some amount of noise. Sorry.
Arjun, I think we lost your screen.
Oh, yes.
Oh, no. Okay.
Okay,
No,
never mind. We lost it here.
Sorry.
It's not on your side.
Okay, awesome. So
Yeah.
I think all good.
Yeah, all good. We'll just figure out how to get it on the screen, but you can continue. Yeah.
Awesome. So yeah, when we're thinking about this imaging system, the observations that we get, right, or the observed signal is a direct function of how our imaging system operates. So if we actually break down our imaging system, which in this case is a camera, there's several hardware and software components that are working in unison. So there's some physical components like the lens and the shutter and the sensor, which each have different physics-driven properties, which influence what our observed signal looks like. So at its core, the data that we collect is actually a direct product of the physics of our imaging system. And in particular, it's how does this imaging system interface with the signal that is coming from the target. So if we can better model what our imaging system looks like or how it behaves, then we have a better way of predicting what our data could potentially look like. So a particular perturbation that we're very interested in studying in MRI, as I mentioned before, is these changes in SNR. And what we want to look at here is how does noise actually manifest in MRI as a function of the physics of this imaging system itself. So typically when we're thinking about noise and using them as augmentations, we add Gaussian noise to our images and train with that. But in MRI, noise is actually manifested in a very unique way that is driven based on the physics of how MRI is performed. So we take a particular sample in our raw data. The sample is the sum of the true signal as well as some additive noise epsilon. And the characteristics of this epsilon are that A, it's complex valued. B, it's dominated by thermal noise, which can be modeled by a zero mean Gaussian function with some standard deviation sigma. And C is that the noise is actually masked. So if there's a data point that I did not sample during the acquisition process, which is how you accelerate your MRI scans, then we can assume that there is zero noise there because we can always mask out any signal that comes from that particular location. So these are certain properties of noise in MR that we need to respect when we're thinking about the augmentations that we design when doing our training.
Just a quick question here. So when you say the it can be masked, is it like is it very obvious that when you have a certain kind of undersampling, you know exactly what mask to use, or is that something that needs to be learned?
Yeah, it's a good question. So you know exactly what undersampling mask you're using at when you prescribe the scan. And so you know that pixel IJ has been sampled or not. So that's how you can figure out if you should keep the signal from that location or drop it out.
I see. Okay, gotcha.
Yeah. So based on this kind of noise-based physics augmentations, we designed this method called Noise2Recon, which is a semi-supervised consistency-based method for noise-robust MRI reconstruction. And because it's semi-supervised, you can train it with both these fully sampled scans, which are labeled data, as well as prospectively undersampled or prospectively accelerated, which are our unlabeled scans. So when we have access to fully sampled data, we can train this in a standard supervised way. And the way that you do that for MRI reconstruction is that you generate some undersampling mask to retrospectively undersample your case space, which is your raw data. You reconstruct that undersampled data with your deep learning model, and then you optimize it with respect to some ground truth reference, which you have because the data is fully sampled. What's interesting is what you do when you don't have any access to a fully sampled case space. So if the data is actually prospectively undersampled, what we do is we generate a masked noise map that respects the physics of how noise is generated in MRI. And we augment our case space with this masked noise. So we add it like we would add standard noise in MRI. And we reconstruct that augmented scan with our deep learning model. We also reconstruct the non-augmented version of the scan and use this as a pseudo reference for optimizing the augmented version. So here we're enforcing some kind of consistency between the reconstruction of our augmented input as well as the reconstruction of our non-augmented input.
I have a quick question here. So in your self-supervised pipeline, how do you ensure that both the reconstructions don't basically collapse, like they actually learn the right reconstruction? How do you train that?
Yeah, it's a good question. So typically when you're doing consistency-based or contrastive learning in kind of low dimensional spaces, right, when you're typically doing it with features, this collapse is quite common. But when you're doing it with high dimensional inputs, there's actually this nice property of based on the loss functions that you pick, where you can actually avoid that collapse based on how the loss is optimized. So if we're using like standard L1 or MSE based losses, you actually have some guarantees of not collapsing to like basically a blank image. And what's nice about this is that there's like kind of a joint optimization of two different objectives. So the reconstruction objective will prevent it, which is like the blue trajectory here. It'll prevent it from collapsing, which is what we would typically see with standard contrastive learning.
Gotcha. So you have in your loss, you have both the consistency loss as well as the reconstruction loss for both the undersampled, the augmented image as well as the non-augmented image. Is that so? You
exactly.
Okay.
Yeah. So the reconstruction loss in this particular paradigm is only with fully sampled data. So what we do is we sample our batch, and then the batch is made up of some fully sampled data, some undersampled data. And then based on that, we have these different pipelines that we pass our model through or pass the data through. And then we kind of do a weighted sum of the two losses.
Okay, gotcha. That makes sense.
Yeah.
Thanks.
Yeah. So when we're thinking about where Noise2Recon could really shine, there's really these two scenarios that we were interested in, right? The first was that we wanted to make sure that it performs well in these label limited settings. So cases where we don't have access to a lot of fully sampled or ground truth scans. And we also wanted to perform well in these low SNR settings. So when we take a look at these in distribution label limited settings, where basically the scans are still have high SNR, we see that Noise2Recon outperforms both standard iterative reconstruction methods like compressed sensing, as well as many of the deep learning baselines, which include supervised learning with and without augmentations, supervised learning based on fine tuning, as well as newer self-supervised methods for MRI reconstruction. And so this is quite exciting because this allows us to show that the semi-supervised approach allows us to reduce the dependency on the amount of label data that we need, but we can still recover quite good performance with Noise2Recon compared to these other deep learning baselines. And in this particular, sorry, go ahead.
Yeah, quick question again here. So
Yeah.
when you say supervised plus augmentations, are you still using the same augmentation that you used for Noise2Recon, or is it a different kind of augmentation?
Yeah, it's a great question. So it is exactly the same augmentation. We just use it in a purely supervised training framework. So we're still respecting the physics of how noise is generated and still using that as a mechanism for physics-driven augmentation.
Awesome, cool.
Which is actually a very important point for the next slide. So thanks for kind of queuing me up, which is that kind of when we're looking at these low SNR settings, as expected, right, Noise2Recon is still performing quite well in these settings because it was trained with these noise-based augmentations. But what's also quite unique is that if we're looking at the supervised plus augmentation methods, which is this orange line here, if we're looking at the SSIM, which is a measure of the structural similarity of the ground truth and the reconstructed image, we can see that it doesn't perform that well, even in noisy cases. So this is quite kind of problematic because if we're trying to use our standard noise-based augmentations in a supervised setting, and it's not actually giving us better performance, then what's the point of performing those augmentations anyway? But in contrast, when we use that augmentation scheme in our kind of consistency-based framework with Noise2Recon, we're able to achieve quite good performance across these different noise levels. And just to make sure, can you guys see my cursor?
Yeah.
Awesome. In particular, when we're taking a look at Noise2Recon, what we did is we trained all of these different methods with a particular noise range. So we sampled sigma values for noise between 0.2 and 0.5 during training, which is a shaded region. But Noise2Recon can still generalize well to noise levels that are outside of that range at inference time. And this is quite important because we can't predict every possible noise level that we want to generalize to at train time. So we want to make sure that we're building in this implicit robustness to even out of distribution noise levels. These are noise levels that we don't typically see during training. And if we take a look at the actual images, what we see is that Noise2Recon is able to recover the structural information in the image better than any of the kind of deep learning and even compressed sensing based baselines without excessively blurring the image. So typically when you perform denoising and you're optimizing some L1 or kind of MSE loss, you're going to sufficiently start blurring the image, which is what you start seeing with the supervised plus aug method here, where there's a lot of blurring across kind of this direction, and even some of the structures here are quite blurry. With Noise2Recon, you're actually able to recover that structure with kind of quite high fidelity. And what's pretty interesting is that if we take a look at the ground truth slice, so this is like kind of the ground truth reference that we're comparing to, this is quite noisy. So this is an edge slice of our scan where the sensitivity maps are not great. So you end up having a very low SNR. With Noise2Recon, you can actually denoise that scan and recover the underlying structure quite well. So this is quite useful because if we can even kind of push the boundaries of the denoising while simultaneously performing this reconstruction, we get to exploit kind of both properties in a single model. And so what we saw was that with kind of in these low SNR settings, as expected, Noise2Recon was performing quite well, but there's several other distribution shifts out there other than just noise, right? And one of the ones that are quite common is that we often change the prescription of our acceleration. So how much we're accelerating our scans based on things like how much time we have left in our scan, what is things like the patient size or the coils that we're using. So this is a function that different radiologists set when they're actually scanning a patient. So in this case, all methods were trained with an acceleration factor of 12x. And we looked at how do they generalize to different levels of acceleration. So these are both lower acceleration factors like 8, as well as higher acceleration factors like 16 through 24. What we found was that Noise2Recon also performs quite well when generalizing to these out of distribution acceleration factors. So this is quite useful because if we can kind of still generalize to some other out of distribution setting that we didn't explicitly optimize for with our framework, maybe we can kind of push the boundaries of what kind of distribution shifts we can actually generalize to with the Noise2Recon framework.
Quick question here. I think this is
Yeah.
super cool. But I can't help but notice that like when you're training on the acceleration factor of 12, you seem to be performing slightly better on 8. So I'm wondering if there's like something that you can do, like train it on the highest acceleration setting and see if it generalizes to all other level acceleration settings. Because that would be
Yeah,
like a great way to like just get generalizability across.
definitely. Yeah. So that's actually a very important point that you mentioned, because when you have less acceleration, by definition, I should be performing better, right? So if my performance actually dipped down, that would be problematic, because that means I've over optimized by some extent, even if I'm performing better than other methods, to this 12x acceleration. And what you mentioned about kind of pushing the acceleration factor during training to be very high, that's definitely something that you can do. But something that's maybe more kind of clinically feasible is that if there's many different scans with different acceleration factors that you can collect and make part of your training data set, then that's actually something that you can kind of pipe through the Noise2Recon pipeline and still be able to generalize these different acceleration factors. So the acceleration factors in practice, this was like a simulated scenario, but that we would collect is that we would typically collect a scan that is already 12x accelerated, right? Or we would collect a scan that is 16x accelerated. So in this case, we were simulating those 12x or 16x accelerated scans. But you're exactly right that we want to be able to generalize to these settings, and with Noise2Recon, you can do that because we don't care what is the extent of acceleration on these prospectively accelerated inputs.
So when you're training, so does it mean that let's say you've already trained with like a various levels of acceleration factors. So let's say you're doing with 12, 16, and so on, and like, artificially in your training set.
Yeah.
And let's say you wanted to introduce a new acceleration factor that you want the model to generalize to. Is that something that you can do post hoc, or would you have to basically fine tune or retrain from scratch? What is your,
Yeah.
do you have any question on that?
Yeah. So I would think that we should be able to generalize well post hoc. So in these figures, there's no extra fine tuning done. So this is just, I trained it at 12x, and then at inference, I just had these different acceleration factors. So if this, I expect that this structure would also hold if you train with data at multiple acceleration factors. So you probably wouldn't need to fine tune downstream.
Awesome. Okay. Thank you.
Yeah. So those results got us pretty excited. The fact that we could kind of generalize to some out of distribution setting that we didn't explicitly train for. So we thought, why not push it up a notch, right? So we looked at how can we generalize across different data sets. So in this case, all of our models were trained on a 3D fast-spin echo knee data set acquired from MRIdata.org, which have all of these properties, which is that it's acquired from the knee, the field strength, which is basically the strength of the magnet, was 3 Tesla, acceleration was 12x, and it was proton density weighted. And we wanted to look at how do you generalize to a completely separate data set, which is this fast MRI brain data set, where all of these properties are different. So of course, the anatomy is different, it's a brain. The sequence is also different. So it's not 3D, it's 2D now. There's different contrast, the field strength is different, et cetera. So there's many different sources of distribution shift in this case that we all can't always control for. And so we wanted to see, okay, well, this is kind of pushing the limit of how kind of generalizable our model could be. And what we found was actually quite interestingly that Noise2Recon performs as well as other methods, or in some cases even better. So on the x-axis, we're looking at different contrasts of the fast MRI brain data set. And we can see that for the flare contrast, which is shown on the left side, Noise2Recon performs sufficiently better than all of the other methods. And for the other contrasts, it's performing kind of about the same or even slightly better. And so this is kind of pretty promising, because there's something nuanced here about the fact that we're training with a consistency-based framework with kind of a denoising objective, and that's allowing us to generalize across these different data sets, across acceleration factors, to different distribution shifts that we did not predict we'd be able to generalize to. And I can definitely dive a little bit deeper into this maybe after the presentation, but a lot of the work that's going on right now with diffusion models, looking at kind of how denoisers are good regularizers for general inverse problems. There's some structural information or I wouldn't call it structural, or destructured information in noise that allows us to exploit some of these properties to better pose our distribution during train time, so that it models what we would see at inference time a little bit better. So low SNR settings are fantastic, and there's definitely a set of perturbations that we want to be able to generalize to. But there's so many other perturbations out there in MRI that we can kind of spend this entire presentation talking about. But one of the more important ones is patient motion. So when a patient moves in an MR scan, which happens a lot, especially because MR scans are quite long, standard model reconstructions would completely degrade this image. So here's an example of motion corruption at the top, and then the bottom is an example of what the model would reconstruct. And again, when you have these different kinds of perturbations, you can have compounding perturbation effects. You may have motion and noise. And of course, in this case, these perturbations actually get amplified by reconstruction methods that do not are not trained with to support these kind of physics-based or be robust to these physics-based perturbations. In addition to these kind of physics-based augmentations that we've talked about so far, there's also other families of augmentations out there. So one of them are the standard image-based augmentations that we typically use during training. So these are things like flipping or shearing, rotation. And we know that these are a source of increasing the data diversity in our data set. And what we would like to do is kind of expand the Noise2Recon framework to account for different kinds of physics-based perturbations, as well as these image-based augmentations. And so if we're taking a closer look at the Noise2Recon framework, there's really a single step where these quote unquote augmentation is performed, right? So in Noise2Recon, we augmented our data by adding noise, but in theory, we could just replace this with an arbitrary augmentation box. And that's exactly what we do in VORTEX. So VORTEX is an extension of Noise2Recon, which generalizes it to kind of arbitrary augmentations. And so the top kind of line here is standard supervised learning, which is what we talked about in kind of the Noise2Recon framework. And the only difference in kind of the consistency-based pathway is that instead of noise-based augmentations, we have an arbitrary augmentation pipeline, which I'll dive into in the next slide. So here, the undersample case space is augmented, reconstructed by our model, which creates an augmented reconstruction. And same thing as Noise2Recon, we reconstruct the non-augmented input and use that as a pseudo reference for optimizing our augmented reconstruction. And so if we're taking a closer look at this augmentation pipeline, what you can see here is that we've paired these physics-based augmentations with these standard image-based augmentations. And the reason we separated them out into these different blocks is that the structural properties of how they are applied are different. Typically, physics-driven augmentations are applied in case space. Image-based augmentations are applied on the coil combined image. And another thing is that the properties of what we're trying to be robust to are also a little bit different based on the kinds of augmentations we're using. So in the case of these physics-driven augmentations, we're really trying to model the perturbations that we would see in practice, and we want to be robust to these perturbations, or in our case, invariant to them. And what this means is that the reconstruction of the perturbed or the augmented input should be equivalent to the reconstruction of the non-augmented input. So this is how we would get rid of this perturbation at inference time and still be able to reconstruct our scan. In the case of image-based augmentations, we're really trying to enforce equivariance to these transforms. So in this case, the reconstruction of the augmented input should be equivalent to first reconstructing the input and then augmenting that reconstruction. So the reason we do this is if we, for example, rotate an image, right? So this is similar to if someone mispositions someone in the scanner, so the image looks rotated. We can't expect our model to undo that rotation, right? So we want to make sure that we're still allowing our model to learn from these image-based augmentations, but we're not making it too difficult that it has to remove these particular kinds of augmentations in practice. Another feature that VORTEX introduces is that we have this augmentation scheduler that allows us to control the extent or the difficulty of the perturbations that we induce at later stages of the training cycle. So what we can do is we can make our augmentations harder at later stages during training, so we can still allow our model to learn, which typically kind of the model reaches some steady state after some amounts of training time. But what we found is that when we increase this difficulty level, you kind of increase the training extent of the model as well. So you get this kind of double descent almost, right, in your loss. So Similar to what we observed in Noise2Recon when we're looking at these label limited settings, VORTEX with different kinds of augmentations. So if we only use image augmentations or physics augmentations or a combination of both, we're able to outperform all of the standard baselines. What's also pretty interesting here is that similar to what we observed in Noise2Recon, when we apply these physics-based augmentations in to our standard supervised models, we actually lose a little bit of performance in our in-distribution setting. And so this is, again, a little bit problematic because if I'm applying some augmentations that are reducing my performance in the in-distribution setting, I'm inducing this trade-off that I have to carefully control between robustness and performance in our in-distribution setting. But when you use the same sets of augmentations with VORTEX, what we find is that you're able to kind of improve this in-distribution performance as well. So what this may indicate is that VORTEX, or the consistency-based framework that we use with VORTEX and Noise2Recon, is more amenable to a diverse set of augmentations, and you don't have to carefully control what augmentations you piece together. With VORTEX, we also extended it from beyond noise to also these motion perturbations. And what we found was that in cases of light or a little bit of motion, as well as heavy motion, VORTEX was able to significantly outperform any of the other baselines. And this is quite important because we're able to generalize well to not just noise anymore. We can also simulate different amounts of motion and generalize well to these settings. So really kind of the takeaway here is that if we have a good model for what certain perturbations can look like, VORTEX can probably be amenable for including it in the training pipeline. And so if we take a closer look at some of these sample reconstructions, where we are reconstructing images with motion, which is on the top row, and images with noise on the bottom row, the methods that are trained without any physics-driven augmentations tend to amplify these artifacts, which is expected because we didn't introduce these augmentations during training. But even the supervised methods that use these augmentations during training still have these artifacts. Right? So we can still see some of the residual motion artifacts, which are pointed by the blue arrow here, as well as there's kind of quite a bit of noise still in this gap area in the D. But with VORTEX, we're actually able to recover kind of the high quality image and the structural information in the image without these residual artifacts. So again, this is more a testament to the fact that this consistency-based framework is a bit more amenable to putting these different physics-driven augmentations with image-based augmentations and even the reconstruction objective all in one unified framework a little bit better than the standard supervised methods.
A quick question here. So yeah. I couldn't help but notice that when you compare compressed sensing and supervised learning, somehow compressed sensing is actually performing better. Is that something that you expected? I mean, VORTEX is absolutely beating all of them, but I was just curious to see how compressed sensing was actually performing better than supervised learning in some of the plots that you showed before.
Yeah, it's a great question. So compressed sensing, for those who may not know, is this standard iterative reconstruction approach where there is no kind of training with any data. So you do kind of gradient descent based on certain priors that you expect your data to look like. And in this case, we looked at kind of L1 wavelet compressed sensing, which basically says that the image should be compressible in the wavelet domain. And that's the prior that you use for your optimization. And what we would expect is that if your supervised kind of method is not trained with enough data, it will not even reach closely to the performance of what compressed sensing can do. So compressed sensing really is kind of the lower bound for what we should be hitting. And however much data we need to get to at least that amount is what would quote unquote be like clinically viable, right? Or what people would typically accept in practice. And so what this may indicate is that kind of the amount of training data was not sufficient enough to even exceed the performance of compressed sensing, at least for this particular reconstruction.
Do you think it's viable to include the compressed sensing objective into your consistency-based framework, like add it as another objective for you to optimize for, or would that make it?
Yeah, it's a good question. So there are, so one way of kind of integrating it into the training pipeline is you have some like undersampled data and you reconstruct it with compressed sensing, and now you've created like a pseudo label effectively, right, for your data. The issue is that compressed sensing takes quite a long time. So for if I'm looking at 100 or 200 iterations, which is quite standard for some of these 3D scans, that would typically take about like a minute per slice, and there's 320 slices. So that's 320 minutes per volume. So generating these labels would kind of take quite a bit more time. But another issue is that kind of if we're trying to integrate the compressed sensing loss directly into the training pipeline, it would also slow that down, right? Because we'd have to wait for that compressed sensing to occur at every step. The nice part is that this iterative kind of compressed sensing approach has actually been unrolled into a new network architecture. They're called unrolled networks, which iterate between a regularization step, which is effectively just an arbitrary CNN. So this can be like a UNet or a ResNet, and then a data consistency step. And the data consistency, which is also used in compressed sensing, says that the data that I actually collected should be present in the reconstructions that I'm producing, right? So if my image goes through my CNN and I look at the case space of that reconstructed image, if I actually sampled point ij in practice, right, I actually acquired that point, those points should be similar or almost exactly the same. So that's what data consistency enforces. The issue is that when your data is corrupted, so if you have noise in your image or you have motion artifacts, you don't want to be consistent with that acquired data, right? So you want some kind of regularization approach to be like, we don't want to be consistent with exactly the data we collected, but something like the data that we collected. So in an extension, which I won't have time to go into today, but an extension of Noise2Recon, we looked at unrolled networks, and we were able to actually pose a data consistency step that allows us to train these Noise2Recon and VORTEX models in an unrolled architecture, which you typically won't be able to do, because if you induce these physics-based perturbations, then the data consistency typically fails. But we were able to create a generalization of the data consistency step that allows us to train unrolled networks with the Noise2Recon and VORTEX paradigms.
Yeah, that's very cool. Thanks.
Yeah, thanks for the questions.
So a small question, how large is the data set for supervised?
Yeah, that's a great question. So here we have one supervised scan and 13 unsupervised scans.
Only
so there's total
one scan?
Yeah,
One
just
scan?
one.
Oh, that's the problem.
Okay. Yeah. So each scan has multiple slices, and we treat each slice separately. So if we have one scan in this data set, that's about 250 slices.
Okay.
But that's still relatively small, especially when you're looking at 3D data, and especially when the data is acquired from or sampled from the same patient, right? So typically when you're thinking about gathering more data for increasing our or better modeling our data distribution, we want our data points to be independently sampled. But if the data is coming from the same scan, they're by definition not independently sampled, right? So that we don't actually get a great estimate of our data distribution. So 250 slices may seem like a lot, but in practice, it's actually still quite small because you are only using one scan.
So did you apply your model to some different scanners with different image protocols?
Yeah, we did. So with VORTEX, we also looked at the fast MRI data set, which is the 2D data set. So there's, I think, typically 15 to 17 slices per scan. And they're like, so you may have like a larger number of scans, so that's a bit more diversity. But we also looked at the similar scenario where maybe you only have 10 fully sampled scans, and you have like 30 or 40 undersampled scans. So again, it also the number of fully sampled scans that you can acquire is also pretty limited, because at train time, there's some data that you have, and there's really not much you can do beyond that, right? And then you can maybe do some online learning or fine tuning with data that you acquire later. But when you're first training these models, it's whatever data that you have available is what you're gonna typically end up using.
Okay, thank you.
Yeah, thanks for the questions. So far we've talked about kind of these semi-supervised settings where we have access to some fully sampled data, and we have a lot of this undersampled or unlabeled data. But in many cases in MR, we are always accelerating our scan. So we will never be able to actually acquire fully sampled data. And some examples of this include cardiac imaging or breath hold imaging, which is basically where a patient has to hold their breath in order to be scanned. And you need to make that as fast as possible because you can't expect someone to hold their breath for 10 minutes. There's kind of these new scan protocols that are developed that are purely accelerated. And for the data we typically collect there, we will not have access to any fully sampled data. So we need to really think about how we can make that reconstruction pathway in Noise2Recon and VORTEX unsupervised. So some folks at the University of Minnesota, led by Burhan Yaman, developed this self-supervised method for kind of MR reconstruction. And what they do here is very similar to masked language training, where if you have some undersampled K-space, which you've acquired, you can separate this into a training K-space and a loss K-space. So these are two disjoint sets of your K-space, where the points are points that you have acquired in practice. So let's say this scan was accelerated by 4x, and all of these white points here are actually sampled. Some of them will go into your training K-space, and some of them will go into your loss K-space. And what you do here is that your deep learning model takes in the training K-space, it applies the Hermitian of the imaging operator to get the actual image, it reconstructs that image. And then what we can do is we can enforce consistency with the loss K-space. So this is similar to that kind of data consistency step that we're talking about. But what we've done here is that we've partitioned our already undersampled K-space into these disjoint sets. And then we're training with one of them and then using the other one as loss. So this is very similar to masked language training with like BERT or something along those lines. But this is the application in MR. And it works quite nicely because this follows very closely how we would think about undersampling or accelerating our scans, right? The way we accelerate our scans is we drop some of these data points out and we want to see if we can recover those data points back. So if we're taking a look at kind of this image reconstruction or kind of the Noise2Recon pipeline, what we really want to do is we want to replace this reconstruction pathway with the self-supervised one. And the nice thing is that we can do that kind of quite easily by just putting in the SSDU objective here instead of standard supervised learning. So this is an extension of Noise2Recon called Noise2Recon SS, which is self-supervised learning for robust MRI reconstruction. And this method can be trained without any access to fully sampled scans. So in this case, the red pathway is exactly what you saw before with the noise-based consistency. And with VORTEX, you can, of course, do this with general augmentations. But what's different here is that the supervised pathway that we originally had in Noise2Recon gets formulated based on this SSDU objective. So we take our undersampled K-space, we split it into our train and our loss, and then we pass the training K-space to our deep learning model and then enforce the SSDU-based loss, which enforces that the K-space points that are part of this loss mask are equivalent to those that are reconstructed. So here, this is completely kind of self-supervised or unsupervised. It does not require any access to fully sampled data. So by combining effectively Noise2Recon and SSDU, what we found was that we can still maintain quite high performance in our in-distribution settings, which are these noise levels of 0. So here, there's not a huge difference between Noise2Recon and SSDU. And this is actually quite promising because typically when you optimize for two objectives that pull the optimization in different ways, where denoising will typically blur an image and reconstruction is trying to recover the high quality kind of sharpness of the image, you will typically kind of reach some steady state where you're not really good at both. But what we find is that when you combine N2R or Noise2Recon with SSDU, you still perform well in these in-distribution settings. And as expected, you generalize better to these high or low SNR settings as well. So you kind of get the best of both worlds by generalizing to low SNR settings, as well as being completely unsupervised during training. And what we did is we, again, did a similar analysis where we looked at how does this generalize to fast MRI data set. And we found something very similar, is that when we're looking at these different contrasts and different noise levels, we see that when the noise levels change across these different contrasts, Noise2Recon SS is still outperforming SSDU. And in the zero noise or the high SNR cases, the performance between Noise2Recon SS and SSDU is effectively the same. So here again, we're getting kind of the bang for our buck, even across generalizing to a kind of completely different data set, despite only being trained on knee scans. So just to kind of summarize where we've been throughout this presentation, we first talked about kind of the importance of accelerating MRI and why we need to do it in order to make sure patients are comfortable during the scanning process, as well as increasing the throughput and the overall operational efficiency of performing MR. We also showed with these kind of 3 different methods that consistency training is pretty powerful for this label efficient training. But you need to be careful with how you choose your augmentations typically, if you're going to do this in like supervised learning. But when you choose your augmentations to kind of be this diverse set of physics-based augmentations plus image-based augmentations in this consistency-based setup, you can actually kind of generalize or kind of reap the benefits of these different augmentations or transforms. We also find that these physics-based augmentations can help improve both in distribution and out of distribution performance, where out of distribution is not just limited to the physics-driven perturbations, but it also generalizes to these different acceleration factors, right, as well as different data sets where there's several distribution shifts that are induced. And finally, I think kind of one takeaway that's pretty important is that oftentimes when we're building these methods, we build them in silo. Right? So we think that like we should build this method in a particular way and use that and compare it to some existing baseline. But what we're really trying to show with Noise2Recon and VORTEX is that we want to strive to get this unified approach for doing several things simultaneously. So how do we combine our physics-based augmentations with our image-based augmentations with self-supervised learning as proposed by SSDU? And when we do all of these together, we can actually exploit a lot of the synergy with solving a lot of these objectives simultaneously. So just a quick plug for some of the methods that we've built. All of the methods that we have, as well as the baselines, are available in the Python package Medler, which you can pip install. And Medler is built on top of PyTorch, and it allows you to kind of manage your setup or your environment in a bit more of a nuanced way, which I think is typically pretty difficult whenever you're doing any kind of medical imaging setup. So it has a set of models that you can use for training. It integrates with Hugging Face, so you can do some model management, so you can automatically deploy and version control your models. It also has some harnesses for training, et cetera. And it has both this Pythonic as well as this command line interface. So if you're interested in exploring any of these methods, looking at them as some of your baselines, feel free to kind of check this out or send me any questions if you have any. And there's also this model zoo, which has all of the pre-trained models there. So feel free to take it for a spin. Yeah, so with that, I'd like to thank all of my collaborators. This really would not have been possible without all of them, and they've each contributed in their own way to this project. So I really want to thank them for that. There's 2 kind of papers or preprints that are out right now. One is on Noise2Recon, which includes both Noise2Recon as well as Noise2Recon SS. And then there's VORTEX, which we recently presented at Middle. And if you have any questions or would like to reach out, definitely send me an email or message me, DM me. Happy to always talk more about any of these things. And thank you. Yeah, happy to take any more questions.
Awesome. I guess before we start questions, we can all give Arjun a round of applause for the great talk. Yes, today is the first day we are all gathered in person here, so we can try to give an applause here. But yeah, now let's open the floor for questions, and folks who have any questions, you can just unmute yourself and ask.
I have a question. So when you test on out of distribution datasets, so is that the only test on that dataset do you need to retrain?
No, there's no extra training that's done. It's just inference. Yeah.
So did you test on some other dataset that looks totally different from what you're training? So actually for your first MRI 6 is also little similar. Maybe some contrast, maybe T2 contrast, is that possible?
Yeah. So there's definitely similarities across different contrasts, and of course, like the signal that you observe is a function of the different contrasts that you end up prescribing. But I think kind of what was pretty unique was that there's several distribution shifts that occur in fast MRI. The main one being that you're going from a knee to a brain, which is like a pretty large shift. But also there's a lot of these nuanced physics-driven shifts. So when you change acceleration factors or you change the contrast, You change even the sequence type, so the way that noise manifests, et cetera, is also quite different. And so typically we wouldn't expect these reconstruct or just a model that was trained on some arbitrary training data set to generalize reasonably well to some of these other data sets, right, where the distribution shift is quite large. But a lot of these reconstruction methods actually can do that quite well, and Noise2Recon can do it reasonably well. So I think that was what was pretty exciting for us.
Yeah. So another question, you focus on the consistent loss. So which function you use for the consistent loss? Just traditional L1 or some different things?
Yeah, so we looked at several losses. So we looked at L1 loss in the image domain as well as in the case-space domain. We looked at an SSIM-based loss, MSE or L2 based losses, combination of all three. At the end of the day, we just stuck with something that was simple. And it wasn't like the best for our method by any means. It was the best for some of the others, but that was the case-based L1 loss. And that's what we ended up showing some of these results for.
Okay, thank you.
Yeah, thanks.
I noticed in the VORTEX results, when you combine like image plus physics augmentations, I noticed the performance is actually a bit lower than physics only augmentation.
Yeah, that's a good question. So both here as yeah. So so this is a really good point. So I think the point that I would make is that the standard deviation or the range of error is is pretty large here. So like there isn't really a strong difference between VORTEX with physics-based as well as VORTEX with image plus physics-based. And when you look at the images, there's really not a large difference between an SSIM gap of this much versus like an SSIM gap of let's say like 0.5 or 0.05 or 0.06. What potential, sorry. Oh yeah, I was saying, yeah, what potentially could be causing this decrease is that there probably is still some amount of scheduling that you need to perform between these different kinds of augmentations. So we did see that kind of a standard image-based augmentation versus doing physics-based augmentations, there's still some kind of push and pull between these two objectives or what they're inducing during training. And so what the scheduler or what we're looking at, what we can make the scheduler do is figure out what's like a good way of balancing these image-based and physics-based augmentations by randomly sampling different augmentations in different pairs. So maybe you'll pick 2 image-based augmentations and 1 physics-based augmentation for batch 1, and then you'll change that for another batch. And by interleaving these, instead of doing them all kind of like all physics-based and all image-based, that could potentially help train the model at some of these earlier stages and prevent it from kind of overfitting to any particular kind of augmentation.
Makes sense. Could you explain a little bit about the augmentation schedule? I'm curious, like how that is done.
Yeah. So maybe I have a slide for it, but I don't think I do in this presentation. But yeah, the augmentation scheduler. What we're looking at, so there's different ways of scheduling augmentations. Typically, what folks do is that they schedule the probability of applying an augmentation. So they say, oh, the probability is 0 because initially during training, because we don't need to kind of have a lot of augmentations when we first start training, and then we kind of increase that probability over the training cycle. And that works quite nicely. But what we also found was that it's not just the likelihood of applying an augmentation, it's also the kind of the difficulty or the amount of the augmentation that is applied. So what we did is we scheduled, for example, the noise range. So if the noise range started from 0 to 0.2, we had a scheduler that changed this range over the training cycle. So it's effectively like a sliding window, or it could be like a growing window, right? Where the upper bound keeps increasing over the training period. So the samples of noise that you collect can be harder with later stages. And we tried different kinds of scheduling schemes. We looked at exponential scheduling and linear scheduling. None of them really made a difference. The only difference was that if you had scheduling, that improved your performance versus if you didn't have scheduling. So the kind of scheduler wasn't as important as the fact that scheduling was present.
I see. Thank you.
Yeah, thank you.
Do we have any other questions? So I actually had one So I was very impressed with the fact that you could go from knee to brain, but it's also kind of like, do we want something like this to happen? So I'm kind of curious what the inference pipeline is. Is it like you have, or maybe you can just tell me what your inference pipeline is, and then I will know a little bit more.
Yeah, no, that's a very insightful question. Because my recommendation would be no. If you can train a different model to perform better on a different anatomy or different setting, which you can do if you can train things in a self-supervised manner, then you might as well just train another model for that, right? That's better performing there. I think the inference pipeline that we had set up was like we trained on these knee MRI scans from dataset A, which is from the MRI data, and then there was no external training done. We just took that model and then ran inference with the fast MRI scans. And so the fast MRI had different undersampling patterns, different accelerations, et cetera. I think kind of that was more kind of to see how far we could push the bounds of like what distribution shifts it could handle. But I think it is still kind of something that we need to dig a little bit deeper into and really ask the question, is this what we want to do versus is this something we can do? Yeah.
I was curious, so when you take your pre-trained model, the model that is trained on your MRI data set and then tested on fast MRI, is there like also a two-stage where you kind of put in a loss and then try to reconstruct, or is it just a reconstruction? Like what does inference look like in that scenario?
Oh yeah, it's just, yeah, there's no kind of a few shot optimization or anything like that. So it's just you put in the case space from fast MRI, the sensitivity maps, which are the sensitivities of your coils to different regions in your image. And that all you kind of acquire when you acquire the scan. And then you put that through the model, and then the output reconstruction is what we compared. So there's no extra like fine tuning step or linear probing or anything. Yeah.
Because I was thinking of a different idea, like a good use case for your model, because so let's say you have a different anatomy present, like let's say it's still a knee MRI, but you have like, let's say a nodule or something that you typically will not find out. And so it would be really cool if your model actually didn't perform well on this, because then you can identify the presence of something like that. But it's kind of interesting to me that it actually generalizes like so well across like even more like a completely different anatomy. So I'm just curious like where this is actually coming from. How they're able to generalize.
Yeah, so I think that's a great point. I think that's some of the work that you've really dived into previously, which is like using kind of failure modes in your model as a source of kind of signal about like where you are failing. And I think that definitely can still apply, I think, in these cases. The issue is that we often don't have a great idea of when it will fail. So we try to kind of cover all our bases and try to make it very generalizable across these different cases that we're trying to care about. I mean, the reason I think kind of also for image reconstruction is that the formulation of the problem is a little bit different than classification. And a lot of the inverse problems, so that these are the family of problems where you're trying to recover some underlying signal from some observed signal, and it's not an invertible process, right? So the imaging system that we showed earlier, you can't invert that process with very high fidelity in some of these inverse problem cases. So it makes recovery, image recovery or signal recovery quite difficult. So these family of inverse problems actually have a lot of shared structure. So denoising is an inverse problem, deblurring, accelerated MRI reconstruction, geometric image structuring, or like kind of depth-wise, or like estimating depth from like a 2D like RGB image. Like all of these are different kinds of inverse problems, and they have a very shared structure in how they are typically optimized. And so combining a lot of these different loss functions together, which have similar structures, actually works quite well, and it works quite synergistically. So this is why we thought a denoising objective or any kind of consistency objective would work well in addition to this reconstruction one. And that allows reconstruction. I wouldn't call it to become it's definitely not a simpler problem, but it's a bit more kind of a structured problem where you know what different tasks you can actually pair together in order to exploit some performance for some downstream task. Yeah, that was a very long answer. The fact that kind of reconstruction has this kind of nice property of kind of being able to be trained with these different kinds of tasks.
Very cool. Okay, thank you.
Yeah.
I guess we have, oh, sorry.
I have another question about the SSD loss. Could you explain a little bit how you actually split, like, split into trend and loss? I'm not super familiar with case-based. I guess I didn't know about case-based before, so yeah, I'm a bit like not sure
Yeah,
how you.
Sorry, yeah, definitely. So in like language model training, right? If you have some tokens, what we typically do is we drop out some of these tokens, right? For like BERT, when you're training BERT, and then you pass that through your encoder and you predict what tokens you masked out. So it's very similar here, where your undersampled case space is kind of your tokens, right? Your set of tokens. You drop some of them out. The ones that you drop out are your loss, the ones that you use for your loss, and the ones that you keep are the ones that you use for training. And so kind of at its core, that's effectively what it is. And the rest of these kind of symbols are how do you convert between case space and image space. So A here is your imaging operator. So this is kind of the imaging system that you have. And the Hermitian of A is kind of your best estimate for the inverse of A. So when you, the A operator takes something in the image domain and puts it in the Fourier domain, which is case space. And A Hermitian takes something that's in the Fourier domain or case space and converts it back to an image. So that's all what this operator is doing. That means you pass the image into this deep learning model, and then that image gets spit out by the model. So you have some image that is reconstructed by the model. And now what you want to do is you want to put that back into case space, right? Because the points that you're looking at are in case space. You want to see if these points are reconstructed, right, or recovered based on this the deep learning model. And so what you do is you apply the A operator to this reconstruction. So that puts stuff back in case space. And then you apply the mask that you used to get this lost case space. So here we can see that the lost case space, which is lambda, equals the masking function of lambda times y. And so we apply that same masking function to the case space of our reconstruction. And so now we're looking at the same points, right? So point ij here, the loss mask in the loss case space will be compared to point ij in the case space of our reconstruction. So very similar to kind of the BERT style training where there's particular locations of tokens that you're trying to predict, and you're doing some mass training there.
Okay, got it.
Yeah.
Thank you.
Thanks for the question.
I have a final question.
Yeah.
So did the datasets in your experiments come from normal people or patient people? So did it contain some lesions?
Yeah, it's a great question. So the knee data set is coming from very patient research subjects who are willing to sit in the scanner for a very long time. So that's like very high quality data, and it's research. Like no one has pathology, so it's like a very clean data set. The fast MRI data set is kind of collected from a patient population. So these are patients that came in for scans that signed a research consent form to have their data be collected for research as well. So there is actually quite a bit of pathology in those scans, and it may not be very explicit. So like it's not labeled explicitly like patient A has pathology or not, but there's different kinds of artifacts that are in these. So some of these fast MRI scans already have motion in them. So when they were scanning the brain, the patient started moving, and that's a motion corrupted scan. And so there are labels on kind of what scans have certain kinds of corruption, what are certain like pathologies that are existing in these scans as well. So yeah, this is kind of also a generalization from a very clean data set to less clean patient data set.
So I have this question because if I'm wondering if that's your model can be direct applied for clinical usage. So if you're training for the scanner and your model tests well, so can we directly apply to the scanner to fast imaging? So you cannot anticipate which the patient has kind of other kind of the lesions here. So do you think that it still works here? So
yeah, it's a good question. So that's actually some analysis we're doing right now, which is looking at kind of an extension of all of this is looking at particular regions in the image and characterizing like localized metrics. So We can do that with Fast MRI because they have there's a new Fast MRI Plus, which adds annotations to some of this data. But from what we've observed so far, we tested this also on some other data sets, which is the SCIM-T data set, which is another 3D QDES sequence-based data set that we built here at Stanford. And that has a lot of pathologies. These are also patients that are that are coming in because like they have issues with their knee and they have like kind of degradation of their knee, ACL tears, all of that stuff. And we were able to find that we were still able to recover those pathologies quite well. So it would be terrible if we just remove the pathology from the reconstruction because that's definitely not what we want to do. But we're able to show that, or we're able to find at least that some of the pathology we're able to recover. So some like ongoing work, future work that we're looking into is how can we do this on in prospective cases, right, where we can actually deploy this at the clinic, not to give radiologists these scans, right, but deploy it passively and see how well do we perform on incoming scans in practice.
Thanks. Yeah,
thank you.
Cool. I guess we ran a little over time today, so thanks Arjun for staying and answering all the questions. And we put up the video up on YouTube, and so if folks have any other questions, please feel free to reach out to Arjun as well. And we'll see you all next week. And thanks again for joining us today.
Thank you,
Thank you all. Appreciate it. Bye.